Good morning. Good morning, Go developers. Are you Go developers, right? Is there anyone who does not code in Go? Oh, so many of you. OK. So, well, this talk is going to be even for you. What I'm planning to do is to basically describe why Go is a perfect language, and then show you that Java is, or JVM is a good language too. My name is Jaroslav Tulach, and I work in Oracle Labs in Prague. And we work on GraalVM, which is basically the technology that I'm going to cover. So first of all, Slido. If you want to ask questions, then go to the slido.com, enter the tag GeeCON 2019, and ask. I will try to answer them during the talk. So the sooner you ask, the sooner you get an answer. Back to slides. A long time ago, I founded NetBeans, and I also was the initial architect of the NetBeans platform. And I usually say that during architecting NetBeans, I made so many mistakes that I felt obligated to write a book about that. So I wrote the Practical API Design book, which is a must-read book for every Java developer, because everybody is in the business of writing APIs. Yeah, the book did not make me rich. It's not as popular as I hoped for. But the good thing is that it attracted attention of the guys from Oracle Labs, and they invited me to join and help them design APIs for various subsystems in GraalVM. So that's what I basically work on right now. I'm from Oracle Labs, which is a small part of Oracle. And as Oracle employee, I have to warn you, if you decide to buy Oracle stocks based on my talk, it's your own risk. At the end, we are just a research organization. So what I'm going to cover today. First of all, I will introduce Go language and describe why it's good. And then we will focus on the fact of doing the same thing with Java, whether Java can be good as well. Then there will be a short break, and I will actually focus on the boundary problem, on a problem when you need to call a native code from your Java application. Anybody tried to use JNI? So this talk, the second part of the talk, should be for you. Go language has been introduced by Google, and it has basically been promoted as a better system language than C. The good thing on Google supporting the language is that if you start to code in Go, you can be quite safe that the language will stay and that it will have strong company support. So also, Google is said to use the language internally quite a lot because of its features, like statically typed language, where you can have structures, just like in C. It's compiled, just like C. In addition to what we used to have in C, it has a garbage collector. So in this respect, it's closer to Java. And also, it has built-in support for concurrency. Again, that's something that C didn't have. The really nice thing on Go is that if you take your code and compile it, you get a single executable. And that single executable you can basically transfer anywhere. Just copy it into your Docker container, and it will work. It's self-contained. So it contains everything it needs. All the runtime is in the single file. In addition to that, it also starts fast because it's compiled. And the memory requirements are relatively low. because there is not a huge runtime support around that single executable file. The only thing that is needed is support for garbage collection. And also Go comes with a relatively huge set of libraries to allow you access to operating system. For a while, well, yeah, Go became really popular at the moment when actually Docker came out, and Docker became popular because Docker is written in Go. My colleagues that are talking to Docker and managing Docker tried to use Java APIs for doing that, but at the end they find it out that it's so problematic that it's much easier to talk to Docker in Go. So that also increases the popularity of the language Go. Oops. Okay, so now what I'm going to do is to compare how fast how fast Go is. And first of all, I have to warn you, because, well, comparing speed of languages is a perfect task for cheating. You can always find a reason why some language is fast. If you want to measure speed of Python based on how quickly it works with NumPy, you certainly can, but then you are actually not measuring the speed of the language itself, but speed of the NumPy library, which is mostly written in C. So better, if you want to compare a language, it would be better to do it without built-ins and without those fine-tuned libraries. So that led me to a definition of Turing speed, basically, because every language, real language, has to be Turing complete to be useful as every programming language. And for that, it needs to have if constructs, while construct, or for cycles. So let's measure those. In addition to that, Turing machine has infinite memory, basically. And if you want to simulate infinite memory, you cannot just allocate one array and then play inside of the array. You need to allocate more and more and more, and then clean the memory. So you need allocations, you need garbage collections. So to do that, I basically, to measure and compare the speed of languages, I basically create a project to compute prime numbers. The good thing is that if you want to compute prime numbers, you can actually let the algorithm run for a long time before all the prime numbers are computed. So you can actually fine-tune that algorithm and let it run for as long as you want. So the project, yeah, let's do a demo. So the project is on GitHub /utulach/Sieve, and it contains the Sieve implementation in many languages. One of them is also Go. So let's take a look at the Go language. So this is my first program in Go, and what it does. First of all, it creates an iterator which generates, generates all the natural numbers from 2 to infinity. Then it contains a linked list, and this linked list is supposed to hold all the prime numbers that we found so far. And then we go through the linked list and try to divide the number that we are currently inspecting with the already known prime numbers. If it's divisible, then it's not prime number. If it is not divisible, then we add that number into the linked list. We have a function primes, which you can actually call and get the next prime number. And at the end, we have a cycle. So basically what I'm doing here is computing 100,000 prime numbers and measuring the time, how long this takes. So let's switch to command line. Well, command line. So we have this Go program, and what I can do is to do Go build. Really nice thing on Go is that it compiles quite fast, and it produces the executable. So we have a single file, and that file has something like 2 megabytes in size. And that file is all we need, and we can run it. Starts fast and runs. Well, actually, the runs are relatively stable, and it takes something like 260 milliseconds to compute those 100,000 prime numbers. OK, so now, of course, we are at Java conference. So the appropriate question is to ask is, can Java do better? Well, of course, I tried. So let me show you the Java version of the same algorithm. So we have the generator of natural numbers from 2 to infinity. Then we have the linked list, which contains all the prime numbers, and we go through it, and if we found new prime number, we add it to the end of the list. And then we have the main loop, with, where we can ask for the next prime number, and we actually measure the time, how long it takes to compute 100,000 prime numbers. Oh, and to answer your question, do I use NetBeans? Yes, this is a quiz. What kind of ID is this? Can anyone recognize? Yes. OK. So yes, I do use NetBeans. I have to, for historical reasons. OK, so now let's run the same example in Java. So I need to change directory into Java algorithm. And it's a Maven project, so let's do Maven package, exec Java. So the Maven runs, builds everything, runs tests, and now the Java starts. And as you can see, it's slightly faster. We can get below 100 milliseconds. That means on this example, Java is at least twice as fast as Go. And the natural question is, why would anyone actually use Go? Strange language, slow like hell. So why not stick with Java? And let me go back to slides. And here is why. Because Java has problem. Not many, maybe more. The Java runtime is really huge. We have seen the single executable that contains everything. This is not how it works with Java. With Java, you actually need your jar file, and then you need your JDK. And the JDK contains thousands of files, and you need to carry them all. The other problem is that when you run your Java program, it starts slow. So first, second, it actually does not do anything useful. It interprets at the beginning, basically does profiling, and only later the just-in-time compiler kicks in and compiles the code. And then we can be fast, but it takes time, and especially for short-running programs like Bash script, like those used from Bash scripts, or those used in cloud for function as a service, the necessary slow startup of JDK maybe is a problem. The other problem is the amount of metadata that JDK carries or needs to keep in memory when running your program. So basically, as I mentioned, Java starts in interpreter mode. And then, only then, it compiles and runs your program fast. But the compilers are usually speculative. So sometimes they over-optimize. And for example, if your program loads new class, the compiled code may be no longer valid. And when that happens, the compiled code needs actually be thrown away. And the JDK runtime switches back to interpreter mode. But that requires a lot of metadata. You need to keep classes. You need to keep bytecodes in the memory. You need to have a map between every save point in the compiled code that allows you to return back from the values that are in registers to the objects used by the interpreter. And this basically means that seeing a Java program that occupies less than 20 megabytes of memory is almost impossible. The other thing is that Java feels like operating system. For certain optimizations, the Hotspot virtual machine is using signals. So if you want to take your JDK and put it inside of your program, and actually the program also needs to use signals in some way, they will conflict. When we work on GraalVM, one thing that we created is also a Node.js implementation that is using Java behind the scene. And Node.js is operating system of its own and uses signals. And Java uses signals as well. And we actually need to play pretty complicated tricks to actually chain the signals in the right way. So that's a problem for embedding of the Java applications. And overall, if you just take your application and try to put it in a cloud, and you have one tenant next to each other, Java is not that good for that, because the metadata will not be shared. They will be basically duplicated. On the other hand, Java is great for long-running processes. If you have a Netty server or Glassfish server running for weeks, it can reach the peak performance and can be really fast. But for function as a service, it's not that suitable, at least not the traditional Java. And that's where we are getting to the topic of my talk. Let's take a look at GraalVM, and especially one part of GraalVM called native image. We would like basically code in Java and get the same executable that we get when we code in Go. Okay, let's go to a browser. Oops. And yeah, so in case you find the topic of my talk interesting, then this is the address you should remember, graalvm.org. You can go there, select download, and here you have an option to download two versions, Community Edition or Enterprise Edition. The Community Edition is fully open sourced, built from open source components, free for use. The Enterprise Editions contains certain additional modules. And the great news is that you can actually buy support for this from Oracle, because last week we officially released GraalVM 19.00. And now GraalVM is official JDK provided by Oracle that you can buy support for. Back to slides. So the native image will actually turn your Java into ahead-of-time compiler, into something like Go. How it works? You compile your application as you are used to and package it into jar files. But then you invoke a tool called native image, which will take the jar files and analyze them and compile them into a single executable file, which is completely self-contained. So once you have this file, you can take it and use it without the JDK. It's just self-contained executable. The other good thing on that is that it starts really fast. There is no interpreted mode. So immediately, once you compile your Java or Scala or Kotlin, any JVM language basically, into native executable, you have something that starts like this. The other benefit is there are no metadata, because we don't need to switch back to interpreter, ever. The code is compiled in a way that it handles all the situations, because it knows all the classes of your application. So, because of that, programs compiled with native image actually use way less memory than those running on classical JDK. But in addition to that, we keep all the goodies of Java. We have garbage collector, safety, generics, types. You can start new threads and do concurrency. So all of these goodies are still kept. OK, so let me do a demo of how to change my program and how to compile it with a native image into an executable. So the trick lies in a POM XML. And here, I have a profile which, as part of the compilation, also executes the native image executable with some additional parameters. And as a result of that, we should get a executable in the target directory. So let's switch to Java algorithm. Let's enable the profile, and now do package. So I'm doing this, and it should fail, because right now I'm running on a regular JDK. So the compilation, everything that Maven project usually does was the same. But at the end, we actually failed on generating the native image, because in this JDK, I don't have native image executable. But the fix is simple. I just need to download the GraalVM and tell Maven to use it. So bin GraalVM, Enterprise Edition 19. So again, compilation tests. And now the native image build starts, and we are compiling the the class files into an executable. Well, compared to Go, this takes longer. But the good thing is that you actually don't need to do this in development. You can develop your application as you are used to with regular JDK. And only when you want to deploy it, you can run this compilation on a continuous integration server, for example. OK, so 30 seconds, and we have the executable. And let me show it. It is safe. So, and the size is actually below 3 megabytes. So from our Java code, regular Java code as we know it, we managed to produce a self-contained executable. So now I can basically I can run the executable, of course, and it contains everything. Starts fast, and well, it's not as fast as regular Java. So if you are interested in like top speed, the peak performance, classical JDK is still better. But if you need fast start and decent performance, something like 10% slower, this might be the solution you are looking for. Questions? Oh, perfect. Thank you for them. Why GraalVM uses OpenJDK of EG Hotspot instead of Hotspot? Well, there are two versions of the GraalVM. The community edition is built on open source stuff, so that means OpenJDK. The enterprise edition is actually built on the Oracle JDK binary. But both of these JDKs, like OpenJDK and the JDK from Oracle, are built on Hotspot. Hotspot is still the technology in there. What GraalVM does actually is like replace C2 compiler with Graal compiler. So that's the basically only change when you are running in classical mode. In case of native image, the system is basically completely different. So does GraalVM do the same optimization as Hotspot's JVM? Is there a JIT compiler? Yes. So the JIT compiler is called Graal compiler, and it is supposed to really work well with modern code. So if you are using Scala, or if you are using a lot of lambdas in your code, the Graal compiler can usually deliver better code. And again, here I'm talking about running in classical JDKs. Because if we look at GraalVM, then you may recognize it looks like JDK. So if we go into the bin directory, it contains all the things as classical JDK does. Just in addition to that, we, for example, have the native image. So there are, and also Node That's something I mentioned as well. So it's an enhanced JDK, but otherwise it's fully compatible if you are running with in the JVM mode with Java. The compatibility should be 100% without any problem. What about dynamic class loading? So when we are talking about native image, dynamic class loading is not there. I will talk about it. Will there be a Windows version of Graal? Actually, yes, there is. If you go to the Enterprise Edition and try to download it, here are the Linux and macOS versions, but if you scroll down, here we have an early adopter preview for Windows. So actually, yes, you can download it and try it. Feedback welcomed. Go looks good to test a prototype, but Java is more readable and common on production. Is there any converter from Go to Java code? Well, the Go program that you have seen is my first Go program, so I don't know. I just was interested in the runtime aspects of Go, not at the language itself. Can you choose different garbage collector after native code has been compiled? Garbage collector, GraalVM, or the native image, contains built-in a garbage collector, and the garbage collector is kind of trivial. It's not the most fine-tuned garbage collector. What we are currently working on is integration of G1 collector. But I cannot promise any date. I don't know whether the work really started and what is its status. What are the reasons for small performance trade-off compared to regular JDKs? Okay, so why the algorithm is running is slow by 10% compared to JDK? Well, the thing is that the ahead-of-time compilation cannot do as much inlining and maybe also other optimizations as the JVM can do. So because using static analysis, it may not have enough information for all the optimizations. On the other hand, what we have in native image enterprise is bin native image help is something called PGO. So what you can do is actually let your application run PGO. Grep PGO. No. Well, I thought it's going to be here. Fine. So what you can actually do is to run your program, collect profiles from sample run, and then use those profiles to feed the native image with additional profiles. And that can actually speed up the execution by 30%. I have an example of that in some other project. Is it possible to create executable for Arm? Not right now, but companies are working on it. Actually, there is a huge interest from the Arm company, and they have dedicated engineers to make that happen. So again, I cannot estimate, but it should happen one day. Does Graal support C-like structures? Well, yeah. So enough of questions. I will move to the presentation because I hope the next sections of the presentation will actually answer some of these questions. So native image has limitations. By compiling into native code, you are actually generating native code. And native code is different for Linux and for Mac and for Windows. So one thing that happened to my colleague was that he actually was using Mac, compiled the executable, and took the executable and put it into a Docker. And it crashed. Of course, because in Docker, the Docker is built on Linux, so you cannot transfer executables like that. But of course, the best thing in this case is actually compile inside of the Docker. So the other drawback is that there are no metadata at runtime. I actually mentioned that it's a benefit. But of course, well, has some limitations. So for example, what you cannot do is to use reflection. By default, it's off. And that helps us to do more optimizations, because if we just allowed you to do reflection and call any method, just most of the optimizations would be disabled because of that. But what you actually can do is to actually tell during the compilation what classes should be kept for or made available for reflection. It just needs to be specified manually. The other problem is that this is not full-featured Java. It does not pass the TCK. So you actually need to adapt your libraries. You need to adapt your program to run in native image. But on the other hand, there are significant applications that can run in native image. For example, we managed to run Java C. We managed to run Netty. And we are using Netty, for example, in Helidon projects, which is Oracle way to do microservices. And other projects like Spring or Micronaut are also experimenting with GraalVM support, and they are relatively successful. On the other hand, Swing is probably unlikely to run or be compiled into native image anytime soon. It's too dynamic. It's based on reflection and so on and so on. So that's probably not going to happen anytime soon. So here is a summary in middle of my talk. Well, actually almost at the end. GraalVM is production ready. You can download it right now. And native image will help you to transform your Java code so it is ready for cloud. It will start immediately. It will have lower requirements on memory, and it will be compacted into a single executable of reasonable size that you can basically transfer between system and Dockers and containers quite easily. So that's the first part of the talk. And now let's do the other stuff. Let's talk about interconnecting JVM, the classical JVM, with native code. So the problem here is that the JVM code is actually heavily optimized. It's JIT profiled, compiled, and can achieve really huge speed. The same can be said about the C libraries. They are also well optimized and compiled well. But actually, the JVM doesn't know anything about the C libraries. So there is a boundary. When you actually need to call from JVM to the unmanaged C code, the JVM needs to do a cleanup. It needs to save all registers. It needs to unregister interrupts and who knows what. I actually heard that it's something like 100 of instructions that needs to be done before the JVM leaves into the C code. And some similar amount of instructions when the JVM returns back. So this cannot be fast, especially when you are switching in the boundary quite frequently. You will see a performance penalty. So in order to demonstrate that, I created a Matrix the Ultimate project. Again, it can be found on GitHub. This time it's GitHub/Jaroslav Tulach/Matrix Ultimate. And here is some description how it works, but let's demonstrate it. So okay, I don't need the terminal, I think. I'll close all the program. Okay. So when I was thinking about some reasons to create this project, I wanted to demonstrate a case when you actually have some good C library and you want to use it from Java. And then you find out that something in the library is missing and you actually need to code that in addition, and you want to do that in Java. So the library that I found is Gnu Scientific Library, and it contains this header file for matrix manipulation. So here is a type structure, C structure GSL matrix. And here is a lot of operations that you can invoke on it. You can allocate a matrix. You can access the matrix. You can read elements or change the elements, usual stuff. So if you actually want to use this from Java, then you need a way to somehow like bridge the application. So for that, I created an abstraction. And the abstraction is a Java interface, Great Scientific Library. It actually does not describe what is the actual structure that represents matrix, but it describes the set of operations that I need from my code. And how my code then looks like. So here is example of dumping. So if I want to dump the matrix, then I create a class, and that class contains two things. It contains the Great Scientific Library, which means the operations, and it contains the matrix. And then it can actually execute some algorithms on the matrix. So in this case, it actually prints out the content of the matrix, or part of the content in the matrix. OK, let's run it. So if I do it in a trivial way and use JNI, which is a comfortable way to access C structures, it actually will run for something like 5 seconds. OK, so what I'm doing right now is basically I'm generating the matrix, 1024 by 1024, and then I'm filling it with zeros and ones, and I'm trying to find a biggest square of the same values. So this is 4 times 4 square with all zeros. And for that, again, I have an algorithm, which is actually an interesting algorithm. And it basically uses the same style. So GSL is the set of operations, then there is a matrix, and we are actually searching the matrix and inspecting each field. And the problem here is that every time we actually call get, we are switching from Java to C to actually read the content of the matrix. And that's slow, especially when you do it a million times. So it's as slow that it takes 5 seconds with the trivial JNI implementation. But of course, what I can also do is to take this Java application and compile it into native executable, the same native executable that I demonstrated in the first part of the talk. And the result is 70 milliseconds. So we are something like 60 times slower when we do this connection between Java and native code in the trivial way. So what are the better options? Let me switch back to talk. OK, so if you want to talk to native code, the traditional way is to do it with JNI, Java Native Interface. The thing is that you create Java methods, and you mark them as native. And then on the other side, you write C wrappers around the C library that the Java runtime will then use to connect to those native methods. I don't have example of that because I don't want to write in C in this, definitely not in this presentation. So the other option is to use JNA, Java Native Access. And it's a relatively comfortable library which removes the need to actually write the wrappers. So you don't need to code in C. Let me show you what you need to do if you want to use JNA. So I have implementation of the interface called JNA Scientific Library. And this is what it does. So it defines the native methods. And the native methods are named exactly as the methods in the header file. So GSL matrix alloc, GSL matrix set, that are the C names. And then there is a magic call into native. And the native comes from the JNA library. So here is the magic call. And it basically locates the GSL library in the library path, loads it, and binds these native methods with the C library. So this is really comfortable. It just has only one problem. It's very slow. So if you want to connect to native, this is a comfortable way, but really slow one. OK, the other option is actually use JNI, the Java native interface. But instead of writing the Java, the C library wrappers in C, you can actually write them using Java and connect them and compile them into .so library using native image. Because native image can also generate libraries. It doesn't have to generate an executable, standalone executable. OK, so how do we do it? I have another implementation called SVM, Scientific Library. And again, I need to specify the native methods. But now, rather than letting the JNA to do the magic, I implement them myself. So I actually have this class with methods annotated with C entry point. And that's basically, if you are creating a library using native image, you can have multiple entry points where the C can actually jump into the native image code. And you can give it a name. And here I'm doing a name which is specified by the Java native interface, and it reflects Java. It has Java prefix, then a name of package, a name of class, and name of method. So basically, if I want to implement this method, from this package, from this class called SVM init, I actually need to specify that it should have this C-like name. And by calling this method, we actually jump from the regular JVM into the native image, native code. And the native code can then access the C structures relatively faster. Let me show you how this version, how quickly this version runs. So run JNI. OK, 223 milliseconds, which is significant speed up, but it's still slower than the original speed that we got from the fully native compiled executable. So now we have another option. Why not move the algorithm from the JVM closer to the data? So why not take the same algorithm that I have written in Java and compile it into the, using native image, into the dynamically loadable library, and then the algorithm will not need any boundary crossing when reading the content of the matrix. So yes, that's possible. It's actually what I have done here in find biggest square. So actually, I have defined directly compute via SVM, native method. And here I'm basically switching from the Hotspot JVM into the native SVM. And the implementation is here. It actually uses the same algorithm to compute the result in the native code. And as you can guess, now there is basically just one boundary crossing. We call into the algorithm, like here, and we jump into native code, and then run everything in native code. And the result is 70 milliseconds. So this is also a way how you can actually use native image to get you some flavor of Project Panama, let's say. So if you need fast access to C structures, native image can be quite handy to that. Accessing C structures, that actually was one of the questions. So how can we access C structures from SVM? OK, here is it, I think. Not, here is it. raw scientific library, I'm sorry. Okay, so what you need to do is to use annotations coming from org GraalVM native image package. And here you can actually describe how the C structures look like and allow your code compiled into Java code, compiled into native image, to access the C structures. So what we are doing is we are telling the native image compiler that there is supposed to be a C structure called GSL matrix, and it has two fields, size 1, size 2. And also we are saying, okay, there are C functions, GSL matrix, GSL free. And if you do that, you can actually, from your Java code, call into the C code quite easily. Okay, next thing. Yeah, let's skip that. I wanted to do a shameless promo of my book, but we are running out of time, so just buy it and that's it. Okay, so this is a summary. GraalVM can help to shape your Java code to be ready for the cloud. Start fast, have low memory footprint, and be self-contained in a single executable. That's the first part of the talk. The second part is basically saying that it allows you to do effective access to C structures. And it actually somehow allows the Java to be used as a universal language, because you can use it as a system language to implement the native part of your application. And usually, I end up with saying, go, Java, go. But let's also check some questions. So let me switch into GeeCON. Here are the questions. Does GraalVM support C-like structures? Yes, it does. What are the known limitations regarding which apps can be compiled into native image? Well, if it's too dynamic, uses a lot of reflection, it will need some tweaks. In general, I would say that if you want to compile your application, you will need to do some tweaks. It's not for free, but it's doable. Is it possible to create executable for other platforms like ARM? Not right now, but it's being worked on. What are the supported operating system for generating native executables? So right now, Linux 64, Mac 64, and the preview version allows you to compile for Windows 64-bit. And the rest is in the works. Is there ARM, Raspberry Pi for support for native image? Not yet. It's being worked on. Cross-compiling in GraalVM. What does that mean? Oh, I see. Compile for another operating system. Yeah, it should be possible, but I have a feeling it's not easy. So the easiest solution is to basically compile inside of a Docker. If you are targeting Docker, then have a Docker image which handles the compilation. And actually, there is a Docker image like that. So you can search Docker Hub for GraalVM native image, and you should get an image ready which contains all you need for the compilation. Does GraalVM support calling native C++ code? Well, C++ does some name mangling, so that's a problematic thing. But if you use extern C and name your or export the C++ symbols under reasonable name, then yes, calling that should be quite possible. So that's the last question. So thank you for your attention, and go to graalvm.org. Thank you.